Alrighty, let's get going today, shall we? Let's get going. Let's see if everything's working. Good. Right on, folks. Good morning. Good morning, everyone. I hope you had a lovely weekend. Sorry about having to reschedule our stream yesterday to today, but I was volunteering with Grad. Hello, hello, hello. Good morning. Thanks for chiming off in the chat right now. Please remember that to. Sorry. Please remember to follow the link in the video description for attendance and stuff like that so that we can get going. Hope you're doing well. I'm just a little tired, but everything is going pretty solid. Let's get started today, shall we? Because got a lot that I'd like to do. So, hope everyone had a nice weekend. It's good to see you all. It's been a while since last Thursday, I believe. Today my main plan is to go over some answers from the quiz that you had a few weeks ago, so that those of you who missed them can learn from your mistakes and potentially look at some redos. But we'll talk about that in a second. This is the last week of distance learning, full on distance learning before the voluntary return to school next week. So that's pretty interesting. Let's go over the plan for this week though right now, since there's a few things going on. So today, like I said, we'll go through the answers for the energy quiz. It might take us a bit more than just the stream today because I don't want to I don't want to rush through this, and I also don't want to make the stream too long. So just we'll play it by ear. Wednesday, I've got my question and answer stream. So if you have any last minute questions about your energy development project, that'd be a good time to come in and ask them. Well, of course, you can ask them during the stream though, so just keep that in mind. I am present. I like that. That's so to the point. Can you read this? Yes, I can read that. Thursday, we've got a few different things going on. We'll have our next stream where I'll most likely wrap up some of the answers on the energy quiz. And if we have time, I might introduce the Big Bang Theory. If not, we'll just push that to next week. But we are definitely going to look at that. So don't worry, I'm not going to pull a friction on you all and push it back like 2 weeks. Also Thursday, I believe it's from 3 to 4 p.m. So it's immediately after school would be. I'm hosting a little stream about going back to school in case you want to ask me questions about that stuff. Should have some more information about that as the week goes on. So should be neat. And plus it'd be nice just to chat. I might end up doing something fun at the end of that stream, but we'll see. We'll see. And then Friday, your energy development projects are due. So don't forget about those. Also, remember that project, well, it is like a nice chunk. It's not like a beefy project per se. I believe your energy quiz for perspective, it was worth more. So just keep that in mind as you're allotting your time, because there's a lot going on right now. There's a lot going on. Whoa, let's not do that. Bump up my views by having my secondary stream on over here. There we go. That's better. All right, so let's get into this stuff so that I can get you out of here faster rather than taking forever. I'm going to work through these answers in OneNote, and I just want to let you know that, let me see if I can do it here. So if this, I cut off a bit of the screen right now for Teams, but that's fine. So this is our team for our class on Microsoft Teams right now. I'm just in the Files tab, but if you go and you click on Class Notebook, it'll take you to this screen, and then fun little tidbit over here. If you click on this little arrow over here, it actually gives you some more options. And what I've been doing since we started these streams is I've kept our little like agendas. So like here's one, for example, from April 16th. So if you go to this area and you scroll down right in this column over here where my mouse is right now, if you scroll down all the way, you'll see a section called energy quiz answers, and you can go and refer to that if you want to go touch base and you don't want to reload the stream. So just keep that in mind. I'll also, once I'm done with all these, I'll post them to Teams so that you have them all in a document. Okay. So let's get going, shall we? Let's get going. So I'm going to go back to this. Actually, hold on. I need to stay with this for a second, and I'm going to go to energy quiz answers. There we go. And now we go back here. All right. So the best way for me to do this right now is if you have like your version of the quiz open some way, because I'm going to just start with question 9 and work my way through all of the questions. I want to do all of them because I want to. There were some that more people missed than others, or there were some that more people got incorrect, I should say. But I feel like if I just skip over some of the questions, it's not really effective because I want you to see how I, again, organize my thoughts for these. So just keep that in mind. Keep that in mind, okay? All right, let's do this, shall we? So I need to fire up my quiz over here so that I can see what's going on too. All right, let's do this. So question 9 was the one with the cheetah. Question 9 was the one with the cheetah. Lovely. Love cheetahs. They're beautiful animals. Absolutely gorgeous animals. Is Wednesday's stream for Science 10 or all classes? So it's for all classes. It's just a question and answer stream. They haven't been very, I was going to throw this out there. They haven't been very well attended. So if you come and you have some questions, chances are I'll be able to work with you really well during that stream because they're usually pretty quiet if I'm going to be perfectly honest. But that's a good question. I'm just going to increase my pen thickness here because it's kind of bothering. That's too thick. That's way too thick. Let's do this. Let's go right in the middle, 1 millimeter. Oh, it's beautiful. Okay. So question 9, we've got a cheetah, and cheetahs can run very briefly with a speed of 31.0 meters per second. That's pretty fast. We'll convert that into a more like an easily visible metric in just a second. And they have a mass of 47.0 kilograms. So remember, these are rather large cats. We're just going to calculate straight up what the kinetic energy of this cheetah is whilst it's running. All right. So this one's nice and straightforward. We're just going to plug and play all of our values into our equation for kinetic energy, which is 1/2 mv squared. Wow, that is not how you do an equal sign, Mr. Potch. So if we plug this in, we have 1/2 times our mass, which is 47, times our velocity, which is 31, and we square that value. And we put this all into our lovely calculators, and you get 22583.5 joules. So 22,583.5 joules of kinetic energy, which was C, I believe, on your quiz. I had a lot more success marking these. I had to essentially, because each question on the quiz had an answer associated with it, a correct answer associated with it, even the non-multiple choice ones, but I marked all quizzes individually, so it's not like the program marked them for me. So even if you, for the other questions where you had to like type in an answer, even if you're off by like a decimal place, or not a decimal place, by like a few numbers, then I usually accepted that. So keep that in mind. So that one was nice and straightforward. I like the next question though. So question 10 was, what is the velocity of the cheetah? But instead of in meters per second, which we have over here, 31 meters per second, I wanted it to be in kilometers per hour because that's something I believe we're better used to using. It's easier for us to see or visualize velocities in kilometers per hour. So how are we going to do this? And this is just a good trick to know because especially if you progress into physics later on, doing unit conversions is extremely important. So we have 31 meters per second. So I'm just going to write that like this. So it's 31 meters. That's the distance that you travel in 1 second. Good morning. Yeah, thank you for saying that. So what I'm going to do is I'm going to use some conversions between like meters and kilometers and seconds and hours to kind of rejig this value. So what I'm going to do first is I'm going to divide this by 1,000 because there are 1,000 meters in 1 kilometer. Okay. The reason why I put my 1,000 on the bottom is because I actually want to cancel out my units because you can do that very easily when you're doing unit conversions. So now instead of in meters, I'm looking at some unit in kilometers, which is what we want to be in. The next thing we need to do is cancel out our seconds. So there are 60 seconds in 1 minute. So again, I put the seconds on top here because I want to cancel out my unit size. And then we have finally 60 minutes in 1 hour, which means that if you punch this in your calculator, you get that is not correct. you get a final answer of 111.6 kilometers per hour. So that cheetah's moving. That cheetah's moving, eh? So just a quick little refresh of how to do that. It's not the end of the world, obviously, if you missed that question, but it is good to know how to do this in the future. It is good to know how to do this in the future. All right. So let's move on to number 11, because number 11 is pretty straightforward as well, because it's just asking you to calculate potential energy. So let's look at this. So we have an anvil, and its mass is 30 kilograms. Okay. And it's on a hill, and the height of the hill is 80 meters. Okay. So what we're going to do is we're going to calculate the potential energy. And I'm just now realizing that you cannot see what I'm doing because my head's in the way. So I'm going to scroll up a little bit. So this, again, it should be relatively straightforward, because remember, you were provided all the equations for potential energy, kinetic energy, stuff like that. So your equation for potential energy is PE equals mgh. I'm going to use this equation instead of the one that is PE equals WH, because we're given a mass right here. So we can plug that right in. So this is pretty simple. We have our mass of 30, and G is always 9.8 because we're on Earth. And then our height is 80. So lo and behold, we get a final answer of 23,520 joules of potential energy. So that's how much energy the anvil has while it's resting at the top of this hill. So that, again, the correct answer for this on your quiz was C. So that's one part of this question. The second part was just, I asked you this question to see if you could do another unit conversion. This time, and this was for question 12. This question I just asked for the weight of the anvil. So mass and weight are different. So the weight of an object, if you remember, so the weight of an object is the object's mass times the acceleration due to gravity. So really, we've already pretty much done all the hard work for this question. So all we need to do is 30 times 9.8. And the answer for this is 294. And this is where I saw a bunch of issues. The units that you use for weight are newtons. So N equals Newton. I'm going to capitalize that because otherwise that's going to bother me. There we go. So that's a Newton. Okay. So again, that's why you go into space. I feel like there's like a test flight today for like the SpaceX program, and they're actually going to launch people with the rocket. So you go into space and you're fully in space. There is no gravity, so there is no acceleration due to gravity, which means that you are now truly weightless. But you still have mass. You still are yourself. It's not like any part of you is going away. So that's a good example of what the difference is between weight and mass. All right. Let's do another potential energy equation. So this is 13 here over here. So this time we've got a table, and it's got a weight of 98 newtons. So we don't know its mass right off the top of our heads, but we could calculate it if we wanted to. And this table is sitting on the top of a hill that's 21 meters high. We're just going to calculate the potential energy here. Okay. So this is another relatively straightforward one, because we can use our other potential energy equation. So P equals WH. So W is 98 and H is 21, right? So we look at all of these together, and we get a final value of 2,058 joules of energy. And I believe that was option A for this question. All right. So hopefully what you're seeing right now is these first few questions are kind of just, they're like warm-up questions. We're just calculating kinetic energy, potential energy, doing some unit conversions. This is what I do on all my quizzes and tests, is where the first few questions are meant to get you like in the groove, so that you can get off to a good start. Bonjour. Wow, that's interesting. I wonder how many people are watching the thing, the like grad thing today. That is what I got, but it said it was wrong. So even if you got just look over your quiz one more time, and if you notice that you got the question wrong, but you still got the points associated with the question, what that means is that, like for example, for this weight question, so for question 12 over here, you needed to get this 100% correct on the quiz. You had to write down 294 space capital N. And that's why I hate these things when they automatically mark them, because let's say you put 294 space Newton or 294 space N or just even 294 N as one thing, that would be marked as incorrect. So what I did is I went through and I checked to make sure that even if you wrote like 294 like lowercase n, that I still gave you a point. So go ahead and check your quiz to see that that question, and you should be able to see your mark associated with it. It'll be like either 0 if you got it wrong or 1 if you got it right. If you notice that you still got it right, but there's a 0 next to the mark, just like email me or chat with me on MS Teams so that I can go over it, because I might have missed it. I'm pretty sure I caught most if not all of those. But again, if that happened to you, just let me know and I'll look over your quiz and we'll take care of that. Okay. But yeah, that's a good point to make. That's why I don't like these online quizzes, because they're so strict with how they set up the rules. But that's all right. All right, let's move on. So we've done a few kinetic energy equations. We've done a few potential energy equations. So it makes sense that we go to question numero 14 and we look at a thermal energy equation. So this question is asking how much heat is released. So we're going to calculate our Q value here. When you have 0.03 kilograms of water, and it starts at a temperature of 96 degrees Celsius and it cools to a temperature of 25 degrees Celsius. Okay, so there's a few options. This was a multiple choice question. I'll just bring it over here so you can see it. So it's question 14 right here. So you got a few options over here. You can see right now that this value is the correct one because it's got the little check mark next to it. But I actually gave you some hints that you could hopefully use before you even start calculating your answer. Asking for heat is released. All right, so we know it's going to be Q. But if you remember, Q can either be positive or negative. It's positive if the material or fluid that you're working with is increasing in temperature, or if it's decreasing in temperature, that means the Q value is going to be negative. So since we've got our water and it's cooling from 96 to 25, that means that automatically this answer has to be negative. So it can only be either option A or option C over here. So let's see exactly what this is going to look like. All right. The first thing we need to do is we need to figure out which equation we're going to look at. So that is Q equals mc delta T, right? We know what mass is. We know what the specific heat of water is because I told you in the question. It's 4180 joules per kilogram degrees C. Why is it so slanted like that? That's really frustrating. We can calculate delta T really easily. So delta T, if you remember, is our final temperature minus our initial temperature. All right. So our delta T is negative 71. So if we plug in all of these values, we have 0.03 times 4180 times negative 71, which gives us a lovely answer of negative 8,903.4 joules, which was option C. For this question. All right. All right, so again, you can use some tricks, and I just wanted to show you this one because this happens for a lot of multiple choice questions. It doesn't matter if you're doing these for science or socials or for other classes, is that oftentimes you can eliminate many of the potential answers just based off of some general knowledge that you might know. All right, so that's a nice little trick. Let's see. I'm going to just pause for a second and make sure I'm not missing any questions. It's funny because I actually yesterday I was at grad and I read some of your siblings um like names and blurbs. That's pretty fun. That is the most fun I've had in a long time. All right. So are we good to move on? Just gonna set this up over here. I'm not gonna move on just quite yet. So yeah, like I said, I'm going to go through all of these answers during today's stream and Friday's stream. I imagine most of you are probably keen on me reviewing the last few questions. So that big roller coaster question and the one where you're throwing the ball in the air and it's coming back down. Those were the questions that were definitely missed most frequently. But the reason why they were missed was not because you didn't know how to solve them. It's because you had to be very specific with how you set those questions up. And like I said, I'll go through and show you exactly how I solve them. Okay. So let's move on. Let's talk about turtles now. I love the way this question is worded. Though slow on land, the leatherback turtle holds the record for the fastest water speed of any reptile. So yeah, they are pretty fast. What do we need here? So the largest leatherback, it could swim at a speed, so it's got a velocity of 9.78 meters per second. If it's kinetic energy, okay, so we're actually given the kinetic energy over here, is 6,800 joules. What is its mass? What is its mass? All right, so we can do this. We can totally do this, right? Nothing new here. So instead, if you look at your equation for kinetic energy, we're used to 1/2 mv squared, correct? Where we know our mass, we know our velocity, and we plug those two values in to solve for our kinetic energy. But this time we know our kinetic energy and we know our mass, or sorry, we don't know what's our mass, we know our velocity. We know our velocity. So we're going to rework this equation so that instead of Ke equals, it's going to say V, or not V, geez, why do I think we're solving for velocity? We're going to solve for our mass, okay? So let's do that. So the way we're going to do that is I'm going to multiply both sides by 2 first so that I can get rid of this fraction over here, okay? And then the other thing I need to do is divide both sides by my velocity, so velocity squared, so I can cancel those two things out. So now I've got my mass is equal to 2 Ke over my velocity squared. And now it's all a matter of just plugging and playing our values in. So we've got 2 times 60,800 all over our velocity. Geez, I thought I messed that up again. 9.78 meters per second squared. And then if we plug these values into our calculator, we get a mass of 1,271.3 kilograms. That's a beefy turtle. Holy moly, that's a big one. It's a big boy or girl. That's a big, big animal. It's like 10 times the mass of all of us, if not more. Crazy, right? So yeah, the point of this question was to just walk you through, and I didn't want to see people panic when they weren't given like a mass over here, because you can rearrange this equation to the point where you can easily solve for the mass, especially since you know the kinetic energy and the velocity of this turtle. All right. All right, let's move on to 16. So 16 was one where, again, we had to kind of apply the same principles as what we just did with this turtle question, except instead of looking at values involving like kinetic energy, we're looking at thermal energy. All right, I believe. No, I'm getting ahead of myself. 16 is just the one with the gun. So if we look at 16 over here, we have a gun or a dart gun that exerts a force on an object that has a mass of 0.02 kilograms, and it's launched with the velocity of, and it's launched with the gun, and its total kinetic energy is rather small. It's just 4.0 joules. So now we're going to calculate the velocity of this dart from the dart gun. Now, we're still going to base this off of our equation for kinetic energy, so 1/2 mv squared. But much like the last question, we know our kinetic energy, and this time we know our mass. So we need to solve for our velocity here. So the way I'm going to do that is, again, I'm going to multiply both sides by 2 so that we can get rid of this fraction. Lovely. And then I am going to divide both sides by m so that I can get rid of my mass. And then I'm going to take the square root of both sides so I can get rid of the square on my velocity. And I end up getting to, or arriving at, something like this, where it's 2ke over m all taken to the square root. Beautiful. And then once you are at this point, it's all a matter of plugging in the values that you were provided. So if we look over here, we do 2 times, where is my work for this equation? 2 times 4 over our mass, which is 0.02, and we take the square root of this value, and we end up getting a velocity of 20 meters per second, which was option C for this question. Just give me 1 second, I'm going to close my window. There's always some work going on outside, and it's always super loud. So hopefully that makes it a bit more manageable for you. Let me see. I'm catching up on my questions right now. Do you know how we are going to shift between online to in-school learning? Truthfully, no, not quite yet. I'm going to go to school tomorrow and start setting stuff up. And we're having another meeting tomorrow morning to go over, I imagine, what the schedule is going to be like in our policies. But I don't have a firm answer for that, which is why I've scheduled my little return to school stream on Thursday this week, so I can hopefully answer those questions in a bit more detail. That's a good one though. Yeah, I'm not sure exactly. I'm not sure. I'm not even sure if most teachers are going to be in their classrooms either, because I've heard rumors that some teachers, like for me, for example, since I move between classrooms, we might be in like the library or other places like that. Also, like things like the cafeteria are going to be closed as well. So yeah, we'll see. We will see. Alrighty. So it is 11 already. I'm going to do a few more questions because I don't want to, again, keep you too long. I'll wrap this up at 11:10 or 11:15. So that should give us enough time to do at least 2 or 3 more. Okay. So we did 16. Let's move on to 17. Let's move on to 17, shall we? So in this question, we've got a box with a mass of 5.8 kilograms. It's lifted from the floor in your garage and placed on a shelf. Once it's placed on the shelf, it has 145 joules of potential energy when it's just chilling there. We're going to calculate the height of the shelf. All right. So we're going to have to use the same kind of principles as the previous 2 questions, but instead of using our equation for kinetic energy, we're going to use our equation for potential energy. Now, since we're not solving for potential energy, we actually know that, and we know our mass, and we know what G is all the time. We're going to solve for H. So let's look at this equation. We're going to divide both sides by the mass and the acceleration due to gravity so that we can cancel those values out on the height side. And we arrive at an equation that looks like this. So H is equal to PE over mg. And then once you are here, I'm just going to scroll down a little bit. Not that much. There we go. That's perfect. Once we're here, we have our potential energy, which is 145, and our mass, which is 5.8, and then G is 9.8. And then this is going to give us a final value of 2.55, right? Yeah, 2.55 meters. So this box is chilling on a shelf that's 2.55 meters tall. Hopefully you used a ladder to get it up there. Otherwise, you are an extremely tall person and you probably should be playing in the NBA. Just saying. Just saying. Who knows? Who knows? Yeah, you'd be like, what? 7.5 feet? Oh, that's tall. That's a tall person. All right. So again, same premise. I didn't give you your mass and your height. You had to calculate your height. But given this equation, you could rearrange it so that you can easily solve for your height here. Or hopefully easily solve for your height. All right. Let me make sure I'm not missing anything. Beautiful. Attendance, I am here. You're all good. Awesome. Lovely. Let's do a few more. Let's move along here. We're going to go to 18. Oh, yes, 18. 18. Now, I hope you can sense a theme with like the block of questions that we're working at. So these questions, I've kind of given you like the energy value and then one of like mass or velocity or mass and height. And I've asked you to rearrange it. So this next one is kind of along the same lines. We have a mass of 0.5 kilograms over here. It's a block of metal and it's going to absorb 5,016 joules of heat. And its temperature is changing from 20 degrees to 30 degrees Celsius here. And the question is asking to calculate the specific heat of the metal. So again, we've got everything that we need here. We just got to move some stuff around in our specific heat or a thermal energy equation. Now, for this one, we can easily calculate our delta T as 30 minus 20, which is 10. So that's perfect. It should be a positive value because our Q is positive. So that's nice. I love it when these two things match. Essentially, if this is a positive number, then this should be a positive number. If this is a negative number, then this is a negative number. Okay? We're going to take our equation for thermal energy. So Q equals MC delta T. And we are going to solve for our specific heats. So that means we have our Q, we know our M, and we know our delta T. So I'm going to do this. We're going to divide both sides by the mass and our delta T so that these values cancel out. And we arrive at C equals Q over M delta T. Oh, yes. So 5,016 is over, what is this? My mass is 0.5 and my delta T is 10. So our final answer for this is 1,003.2 joules per kilogram degrees Celsius. Oh, yes. Beautiful. Absolutely beautiful. Absolutely beautiful. All right. So again, you had everything that you needed to succeed for this question. We just needed to tinker a little bit with our old equation for specific heat. Old equation for specific heat. I'm late. Sorry, I'm late. I went to run and I'm at Lonsdale Quay. That's fine. No worries. That's fine. No worries at all. I go down by the quay almost every day these days. It's all good. It's all good. All right, so we're getting close. So I'm gonna do the next question, which is kind of like a group of it's a question in two parts, and then I think we're gonna pause for today and leave the rest for Thursday, which is totally fine. It's totally fine. I'm stoked to do. I'm really excited to look at space starting soon. I'm fine if we don't start it until next week though, fully, because a bunch of you are still working obviously on your energy development project, and I don't want to really start a new unit when you're kind of wrapping up the other one. So that'll all work out. So let's move on to 19, shall we? And then 19 and 20. So I'm going to do this as 19 and 20 like that. This one. So we're going to throw a softball with a mass of 0.2 kilograms. And it's going to hit the roof of a room. It's going to barely hit the roof of a room that is 10 meters tall. Wow, that's a really tall room. You're like in a church or something like that. Don't throw softballs in churches or any places like that, though. Assuming that energy is totally conserved and none is lost to friction and air resistance, calculate the potential energy of the softball at the ball's apex. So PE is what? So if you're going to draw this around, you've got your ball over here, and you're essentially throwing it straight up so it hits the roof, or barely hits the roof, all right? So this should be pretty good for us because we're, again, just going to calculate PE. So PE equals mgh. Our mass is 0.2. Our G is 9.8. And our height is 10. Lovely. Love it when this all happens. So this means that our potential energy for the ball at the apex, so the apex would be like right here. This would be the apex. So the highest point that it reaches is 19.6 joules. 19.6 joules. Okay. All right. So this is your answer for question 19 right there. Now, if we look to the following question, which is question 20, we're going to now calculate the initial velocity for the ball when it left our hand. So right as we were releasing the ball, what is that velocity? So to do this, we need to remember our energy conversion. And this is a perfect place to kind of wrap up for today, because a lot of the last questions on this quiz were pretty much energy conversion questions. So you needed to be aware of that the law of conservation of energy. So if you remember, our potential energy for the ball at the top is going to be equal to the kinetic energy for our ball at the bottom, so that when we released it. So in essence, our KE of the ball is 19.6 joules. All right, that's beautiful. That's beautiful. Which means that if we use our equation for kinetic energy, 1/2 mv squared, and we reorganize it so that instead of solving for kinetic energy, we solve for our velocity. I did this in a few previous questions, but when you work this out, you'll get velocity is equal to 2ke over m all to the square root. All taken to the square root, I mean. And then once you're here, we can plug in our kinetic energy value. We can plug in our mass of the ball, and we can solve for our velocity. So we do 2 times 19. That is not a 19. That looks like a 16. I know what numbers are. 19.6. And we divide that by our mass, which is 0.2 kilograms. And then we take the square root of this value. And we end up getting a velocity of 14 meters per second. So I'll underline that right there. Beautiful, right? Beautiful. So this question was really important that you were aware of your conservation of energy law, because you can easily apply that when solving this, because you can calculate your potential energy relatively easily. And then it's a matter of using that value for your potential energy, converting that to kinetic energy when the ball was initially leaving your hand, and then you can calculate for your velocity. Okay? So just keep that in mind. I'm just trying to show you something. There we go. All right, so remember, and I'm just going to switch up my screen right now, so just give me 1 second. Remember that I am updating these answers on Teams. So if, again, this is our class on MS Teams, if you go to, I'll just go and I'll show you this again. If you go to the class notebook right here, and then once this page opens, if you click on the little arrow icon right there where my mouse was, in this little column or section over here, if you scroll to the very bottom, there'll be a section called Energy Quiz Answers, and all of the answers that I just went through are going to appear right there. So don't forget about that. What I'll do is when I'm finished with all of these, I will just, whatchamacallit, I'll just export them to a PDF, and then I'll post that document to our team as well, so that is, you have it in a few different places. Okay. So let's see. Let's wrap it up. So once we redo all the questions in this quiz, I'll allow you to redo certain parts of it. The way that redos will work here is, well, if you're at school next week, that'll be easy because you can just pop in. We'll get it done for face to face. But if you're not coming to school, which is totally fine, you can set up a meeting with me on Microsoft Teams. And what I'm going to do is I'll block off sections of my day where I'll be free to meet with students this way. And I'll get those times to you early next week, hopefully, when I know what my schedule is a bit more. And then we can work through them together one-on-one. Just make sure that your webcam or your mic are working so that I can see and talk with you, because that way you can show me your work in case stuff's not going well. And we'll take it like there. We'll just treat it like redos, like we were back at school almost, except many of you, I imagine, will be doing it through Teams, which is totally fine. Okay. So I think that's more than long enough for today. It's almost 11:15 right now. If anyone has any questions right now, it'd be a good time to ask them. Otherwise, let's go this way. So otherwise, like I said, this week we've got a bunch of little things going on. So tomorrow, if you're having any issues and you want to talk to me one-on-one, feel free to drop into my question and answer stream. It'll run from 12 to 1, I believe. Thursday, we'll finish off the questions on this quiz. So the big ones that I want to go through are the roller coaster question and the last softball question, because those were ones that many people missed. And then Friday, you've got your energy development project due. So there's lots to do. Remember, try to do as much as you can. I'm not going to get upset if you can't do all of the above, but just try your best. Take care of yourself first, and then take care of your school after, because I've been chatting with especially a few of my more senior students, and there's a lot of stuff going on in our lives right now, and that's totally understandable. So the best thing that you can do, if you're like, I have 3 billion things that I'm doing right now, and you know what, Mr. Potch, science just isn't up there with my priorities, the best thing you can do is just send me an email or a chat message on Microsoft Teams, because at least that way you're telling me that you're aware of what's going on, and we can work through it much easier than if you ignore it or you let stuff pile up. So keep that in mind. Okay. Let me just double check to make sure I'm not missing anything. Groovy. All right. Look like we're pretty good right now. So with that in mind, hopefully I'll see some of you either Wednesday, Thursday, or not Friday. We don't have any streams on Friday. Thursday, you have 2 streams that you can go to. There's our Science 10 one at 10:30. And then there's the going back to school one that is at 3. And then after that one's done, I might try to do some fun things. Like I might play some video games, but whatever. That's beside the point. So I hope you have a lovely day today, everyone. Take care of yourselves. If any of your siblings are graduating right now, I hope they're having a nice day. I'm going to go try and swing by the ESC later on today to see if I can catch any of your siblings. And then with that being said, thanks for tuning in, and I will see you all later this week. Take care, folks, and have a nice day. Bye for now.